So welcome everybody. My name is Peter Ohwe. I'm here on behalf of Professor Olubusoye. I want to share my screen. If you can see it, please let me know. I'm afraid that my video isn't working. I don't know, maybe it's because of the strength of the network. If it eventually works, you'll be able to see me. All right, can you see my screen, please?
Yes, I can.
Okay, very well. So we are going to begin today's session by taking us back to like the start of the program so that we'll all be able to know where we stand. A lot has happened and we are like midway into the program. It would be nice if, you know, we are been able to cover the initial content properly. So I want to say that we expect that everyone participating in this course should be on this platform. On this platform, we have the link to the meeting. So every time you come here, you should join here. So sometimes some people complain on the WhatsApp platform that they're unable to join, and they sometimes want us to, you know, give them, once you click on that, you join. So I'm going to stop that, okay, and then come back. So you only need to click on this. All right. So we began this whole discussion by creating this platform. Professor Lubuse created this platform. And then by the 28th of January, he posted the course outline. It is this course outline that I want to revisit so that we will know where we are at the moment. Okay? So we began by looking at introduction to data science and introduction to R programming. The major thing that we achieved there, which was really major, was that we're able to install R console and R studio. Then we tested them, okay, by doing basic data, structures and operations. So we're able to cover this. This is like the foundation of this foundational course. In our second session, we looked at data wrangling and manipulation. We said that data doesn't come in the format that you desire for analysis. So you have to transform data, you have to filter out irrelevant, values and reshape your data. In the third session, which has now resulted in a recent quiz that was posted, we're looking at visualization with R. We set a deadline for that quiz to be next Thursday or thereabout. Okay, and then we are going to give us another quiz on statistical modeling. But the time frame for returning that next quiz will be a shorter time period. The idea behind the quiz is to reinforce what we are already learning. By taking those quizzes, you're able to recall some of the lessons that you have learned, and then in most instances, you have to go back to the videos and the materials to, cross-check and see if you can recollect what was, taught in those classes. So that is an advantage. Okay. So last week we looked at machine learning basics, and actually it was actually, a challenging time for some of us. Some participants expressed their opinion about the content being too advanced, and that was not unexpected. So we agreed that this week we are going to do a recap of the machine learning basics and then add this week's lecture. This week's lecture is about random forest and ensemble methods, which means that if we're able to navigate this week's lecture, we'll have like 3 more lectures. What do I mean by that? We'll have support vector machines, unsupervised learning techniques, And lastly, we, look at emerging trends in data science. You wonder, why did I skip this session 9? Yes, because this is going to be a project. The details of this project will still be communicated to us. I will want to get feedback on, this content that I just shared, so that it will be a real conversation. So if you want to give a feedback, not necessarily on the outline that I've shown, if there's any challenge that we are experiencing, let us share them and see how we can tackle them. Anybody? Okay, good. At any point in this conversation that you feel like you want to make a point, feel free to make that point. So I take us back to, yes, Adesheye Ogun Tiloye, Dr. Prof. Go on, sir.
All right. Thanks for the good job you're doing. I just want to ask this, that after this 10 weeks training program or training, will there be a follow-up to get feedback? Because in all fairness, we need to do our own personal study after each of the classes. May not be readily available, or we may not have readily available questions to ask. But as we study along the way, some questions will pop up that we may need, what's it called? Someone who has gone ahead to answer. So will there be a mentorship or follow-up after this program?
That's a very fantastic question. And I would say it's a timely question, in the sense that even though I cannot really answer that question, because this course has to do with my professor and the rector and all of that. But I'll try to see what I can do. Beginning from today's lecture, I'll begin to share with you platforms where you can upskill. Okay. I'm going to show you at least, just remind me, I'm going to show you at least 2 platforms today that will be very helpful. And remind me again, Dr. Adeseye Ogutile, next week, I can add 2 more platforms. I've had opportunity to use a lot of platforms. So even if there isn't a follow-up, class immediately, you have those platforms to help you. Having said that, of course, if you have issues and you reach out to me, and I'm free, I'm always available to respond to your requests. But on a formal note, we'll have to still pass through the prof and then go to your rector and decide all those things. Did I answer your question well, sir?
Yes, you did.
Okay.
Thank you.
Okay, thank you, sir. So we go to today's session. And the way I want us to, treat today's session is like a review of the machine learning last week, but using a different approach. So I'm going to look for a whiteboard, and this is still consistent with what you were asking. So I'll go to whiteboard, and then I'll, like in 15 minutes, discuss how to do data science. That's the attempt that I'm about to make. How do you do data science? What is the end-to-end pipeline of a data science project? What are the steps in, what is the difference between data science and data analytics, and all of that? Where did machine learning come into data science? Where is the line that distinguishes a data scientist from a data analyst? So I hope you can see my whiteboard. Am I good to go? Can I go?
Yes, I can see it from my end.
Good. Yes, Good. So what I'm going to do is I'm going to call this data science DS. And I want to show you about, say, close to like 10 steps that are involved in a single data science project. This is in preparation for week 9. Today is week 6. So we only have week 7 and week 8 to revise some of these things, so that during the project you'll be able to achieve that, that goal. It's good to build on whatever we have learned. And because of the kind of jobs that most of us do, we might not have that time. And if you don't practice what you have learned, the tendency to forget them is always there. So I will tell you when data analysis becomes data science. What do I mean by that? Data science is like data analysis plus other things. So where data analysis stops, data science continues. So the first thing in any data science task is that there is always a problem statement. Either a problem that you have identified on your own, or a problem that your client has brought to you. So you need to understand the problem statement. If there is no problem statement, you need to be able to design a problem statement. Because if you don't understand the problem properly, you will not provide a solution to the problem. Okay? So I'm going to call this step 1, understand problem statements. Or if you like, understand the business. Be able to, define what the challenge is and what the goal is. Know the aim, know the objectives clearly. I would have asked you to give me an example of a problem that we could tackle, but I thought that might take us some time, because this is not part of the content that we're supposed to cover, but it becomes very necessary. So I said to myself that I'm going to give us an example of a problem. Okay? So there is this task in data science that we refer to as handwriting recognition. Handwriting recognition. Okay, so you and I know that if you are so close to an individual and the person has written you letters several times, it is possible for you to be able to recognize that handwriting because you are human. But we are saying that it is possible for you to replicate that same thing, or it's possible for you to teach your computer, which is now your machine, how to recognize that same, thing that humans can. So data science is about allowing your computer, your machine, to make deductions, predictions, to understand patterns and trends based on data. So the problem statement here could be trying to recognize whether somebody who signs a check has forged a signature. Trying to check if a student, who sat for an exam has impersonated. Trying to trace an individual based on the handwriting. So there's a business problem like that. I can think of many business problems. So when you say business here, it's not about buying and selling alone. It's about situations that require intervention, but now you are using data science techniques to handle it. And I've said before, I'm saying again, that once you get it wrong at the point of understanding the problem, whatever you build on it will not be, efficient. Once you have understood that, the next step is to gather data. And it's important to mention this because as we move into real projects, we are going to see that the collection of data can happen in different ways. For instance, you, the investigator, the researcher, or the data scientist, can actually collect data firsthand, which we call primary data. So you can collect data. If you don't collect data by yourself, it's possible for you to use data that someone else has collected. And if that is the case, we now call that secondary data. Beyond primary and secondary data, you can also generate artificial data, which we refer to as simulation. So there could be more. There could be more. Even in concerning the secondary data, the source of the data, the format of the data, and all of that, because you can collect data even online. Okay, so we have the second step, which for us in this part of the world is always a very difficult step. Data collection is challenging because sometimes it might not even be available. And I want to appeal to my friend, Dr. Adesheye, remind me again, beyond just reminding me of resources that we could use to develop ourselves personally or beyond this session. Remind me to also, show to us where we can get data for practice. And I forget some of those things. So collection of data is the next thing. After you have, okay, so in this case, we need to look for data sets that are being used to train solutions that recognize handwriting. Okay, so I'm not going to talk too much about how to tackle the problem here because we'll come back to it at the end. That will be the last part of our work, this other section of trying to solve the problem and itemizing the process. So step one, we understand the problem statement. Step two, we collect data. Okay, so once your data has been collected, you can now begin to talk about the technical part of it. Because collection of data does not only require technical skills, it also requires, soft skills too. Your ability to collaborate with others, creativity, and all of that. So with regards to the technical aspect of it, we have adopted a programming language called R. R is not the only programming language that you could use for data science. In understanding the problem statement, you don't need to know R programming language. In terms of collection of data, you don't necessarily, because it's possible for you to use R programming language to source data. There are some tasks that you perform in data science, like web scraping, okay? Getting data from the internet. You can use the knowledge of R to write scripts that can help you to collect data for your project. But generally speaking, you could collect data without your R skill. Of course, we are lecturers and we can even collect data as we are in class. Simply going to the classroom to check when people join the class, the agenda and all of that is data that can be useful to make deductions on how gender affects learning data science. But that's a different conversation altogether. So after collection of data, there's a need to structure the data in a format that is proper for data analysis and or data science. So that is what we are going to refer to as pre-processing. So this pre-processing has to do with checking the data for missing values, checking the data for outliers and extreme values, checking the data for, values that are inconsistent with others, checking the data for false values, and all of that issues around restructuring the data is what we call pre-processing, and many more. It's not just the few things that I've mentioned. And at this point, if you succeed at this point, some people say that you would have done 70% of the work. So when we teach these things at times, we could emphasize so much on gathering the skills for data collection and pre-processing. So sometimes some people recommend that your Excel skill is very important. Sometimes people even ask you to learn other, skills like SQL and stuff like that. But for us, this is a foundational class. If you understand the problem, you're able to collect the data and pre-process the data, you've gone far. So what do we now do in data analytics? Where does data analysis end really? Sort of. It ends with exploratory data analysis. You will see that in EDA, the last word in the acronym is analysis. In fact, the last two is data analysis. So technically speaking, when you have reached this point, you have completed data analysis. Now, some people believe that there's a fifth step, and that's why I'm going to draw that fifth step on top of this line. There's a fifth step called visualization. Now, for some who argue that visualization is part of exploratory data analysis, I think I will agree with them. But for others who say, no, visualization is a separate thing altogether, I know where they are coming from. What do I mean by that? When you do data analysis alone, you will need to do visualization, like, making plots, drawing graphs, and all those issues about curves and lines and scatter plots, box plot, and all of that. To understand, details of the data, the hidden patterns in the data, because those pictures, those graphs, they provide more information than text. However, when you now add the other steps that are not necessarily in data analysis, you will see that there are other forms of visualization beyond exploratory data analysis. Because the kind of visualization you do in data analysis is just visualization that you get from the information in the data. So if I want to summarize all I've said, step 1 to step 5 are the steps involved in data analysis. So if you say you are a data analyst, you need now to define the field where you apply, this your skill. Because data analysis does not stand on its own. So yours can be in education, it can be in agriculture, it can be in health, and so on and so forth. So what we are saying in essence is, all of these 5 processes are still part of data science. Moving forward, when you have now, done EDA and visualization, then you now talk about building models. The idea of building models is the start of something beyond data analysis. So data analysis does not, include building models. So what are models? Models are just abstractions, abstract, equations, mathematical formula, relation, everything that has to do with abstract representation of a real world scenario is what you will call a model. A model does not do anything in data science except that it gives us an idea of a real life scenario. So it is when a model is fed with data that it now becomes alive. And the process of what do you call that? Exposing, that's the word. Exposing your model to data, okay, helps your model to learn the hidden patterns, to learn the trends, to understand the details in the data, and then improves over time. So we now said, when it comes to building of models, I'm going to another slide. When it comes to building of models, we are saying that we can use traditional techniques, like traditional statistical techniques, or we can use machine learning techniques. So last week, we began to talk about machine learning techniques, machine learning models, you see now. And we said that we have what we call supervised learning. We said these techniques are such that the models have both inputs and also outputs, but the outputs are labeled. So once the outputs are labeled, you call that supervised learning. We did not end there. We said supervised learning can be divided into 2 parts. We said that there's a regression, and that regression refers to Models whose outputs are numerical, are continuous values, like the price of a house, like inflation rate. And we said the other categories will be referred to as classifiers. So in supervised learning, we have regression models and we have classification models. So that's one group or type of machine learning techniques. The second techniques we call unsupervised learning. And we said the distinction between supervised learning and unsupervised learning is that in unsupervised learning, the labels are not given. So there are no labels. In week 8, we look at examples of unsupervised algorithms or models. And there, we said we'll be talking about clustering algorithms where the models don't have labels, but they can learn. By the time they are exposed to the data, they can see trends and patterns and then decide to now begin to group the data that are not labeled into what we call clusters. So in unsupervised learning, we have clustering algorithms, and they are not the only ones. The last type of learning that we talked about are the reinforcement learning. So if you take away from the introduction to machine learning, is that we have supervised learning where we have labeled outputs. There are unsupervised learning methods where you don't have labeled outputs. And then there is the reinforcement learning where you have an agent, maybe like a robot. And last week we used our pet, your dog, who learns by trial and error. So the agent is in an environment, and then the agent begins to learn by making attempts. When the attempt made is wrong, the data scientists would have figured out how to correct the agent so that the agent will not repeat that unpleasant, action. That's the kind of reinforcement. On the other hand, if the action taken by the agent is the type that you want to encourage, then reward is given. Let's go to our next slide, or go to the previous slide. So in step 6, we are talking about building of models. When we feed the model with data, we don't have the luxury of, testing our model with new data all the time, because it is wrong for you to produce a drug and you say the drug is safe without testing it. So there's a training phase in fitting your model, in building your model, in performing this machine learning process. So that will take me to the third slide. That process, which we refer to as building of the machine learning model, which entail exposing the model to data, can be achieved by splitting your data into 2. You call one part the training set, and you may call the other part the test set. So if, for instance, you have a total observation of about 1,000, okay? It could be any experiment. Okay, you have a total of 1,000. You could now decide to split this data using any convenient ratio. But we have said that at the minimum, the training set and the test set should be equal. But in practice, the training set is always greater than the test set. So we said that if you can take 70% of the data for training and then use 30% for testing. That would be a very wise ratio. But someone might ask, how do I select this? Of course, you select it statistically. Okay, you use randomness. Otherwise, if you don't randomize the sampling, it will introduce bias. And you don't need to learn the heavy maths that's behind it. R already has packages that are able to do that. Then one question came up about how we arrive at this ratio. So we advised that when you have a small data set, you are the one that will determine what small means. Okay, so if we have a population of 250 million in Nigeria, I'm just saying, and you're able to get 100 million people, you have details regarding 100 million people. I don't think that's a small data set. But if in India, they have about 1 billion people, if not more. Yeah, I think India, China, they both have over 1 billion people. I have 100 million, then that is small. So this small that you see here is subjective. It depends on the context. It depends on the experiment that you are performing. So we now said, whatever your definition of small or large is, if you consider that your data is small, then please use a higher percentage for training so that your data, your model can learn enough. So you could have something like 80 and 20. But we went on to say, in some instances, there is another set that is called the validation set. Okay? So it is possible for you to have 80% for training. You could then do 10% for testing, and then you do 10% for validation. It's allowed. In fact, for some people, they refer to the test set as the validation set. We went on to say, if you consider that your data is very large, then it will be better so that you don't waste too much resources training your model. Okay, so you can do 60-40, and you can decide how you want to break the 40 into testing and validation. Brilliant. Okay, so back to that initial slide. There's a slide that we've been following, this slide. After training, the next thing that you should achieve is testing. Okay, you want to find out the performance of your model during the time of training. You want to compare that to the performance of the model during testing. So we said, and even if we did not say before, we now want to say that if the performance of your model during training is poor, then you need to, rerun or change the model that you are using. What am I saying? You see that this process is like a linear one. So by the time you get to building of models, and you now train and find out that you are not getting good results, the reason is that the relationships between the independent variables and even the outcome could be linear. Like a straight line, it could give you a linear relationship. Then it would be better for you to use a linear model like linear regression. But sometimes they can be non-linear, they could even be complex. They can be in very complicated structures. That's why in some instances, you could use several models and then now look at the best performing model. That means you have several alternatives that can learn from your data and you check their performance. But where are we going to? We are saying that if the performance during training is poor, then we say we have a situation called underfitting. But if the performance in the training set is okay, then you move to the testing set and find out that the performance is also okay, then you should adopt that model. That makes a lot of sense. But in practice, we find out that sometimes the performance of our model will be, very okay with in the training stage, But when it now gets to the testing stage, it now fails us. So we call that problem overfitting. This is a huge issue in machine learning. Okay? So if I go back to the question that was asked earlier, remember that this is an introductory course, a foundational course. Overfitting is a serious issue. There are methods for dealing with overfitting, but you should try to ensure that the test results that you get are also equally, high. If that is the case, by the time you discover that your test results are not good enough, you go back, change your model, or you start the training again with the same model by doing, work on the independent variables. So the independent variables are sometimes referred to as features. Okay. So if you see that your test results are not coming out nicely, one way to improve performance is to begin to do what we refer to as feature engineering. How does that work? It is possible that there are some variables, which we call features, that are not really contributing that much. They are just there, as noise. They are hindering the performance of your model. Or, better put, their contribution is not significant. Rather than throwing them away, you can create new features that will incorporate them with other variables. So feature engineering is another branch of machine learning. And like we have said at the beginning, if you are just joining, data analysis ends at this visualization phase. But when you now begin to do training and testing of model and trying to make sure that it fits properly, and you are re-engineering the process, then you have left data analysis a long time. The goal of training and testing a model is to see whether it solves the problem. So what do you do after you've trained and tested your model and you are seemingly satisfied? Then there's need for you to do evaluation. So I need to create an extra slide. We are still looking at supervised learning models. And we recall that we said that supervised learning models can be regressors or classifiers. When you are trying to predict a number, a numerical value, and you want to evaluate, your evaluation has to do with reducing the error. Take, for instance, the real price of a house, which is Y. Let's assume that it is $52,000, 52K, or $52,100. That's the real price. But your model now estimates the price of that particular house as $53,000. It has predicted that it's $53,000. The difference between the actual value and what you have predicted is the error. So there is error, which is the difference between the actual value. Don't forget, we are talking about regression when you are looking at numerical values. So this difference is what we call error. And the idea is to minimize this error, to make sure that this error is as small as possible. If you find the square of this error, okay, and then you now sum, you know how you find mean, you sum and divide by the number of observations. You now have what we call the mean squared error. This mean squared error, when it is small, it means that your model is performing well. Otherwise, it is performing poorly. If what you are looking for is the absolute value, then we change this mean squared error to mean absolute error. But that's not these are not the only metric that you use for, evaluating numerical values. We have other metrics such as root mean square, R squared, adjusted R, and all of that. What I'm trying to do is to make a distinction between evaluating when you are running regression algorithms or models because you are trying to predict a numerical value. Let me pause and ask, am I speaking too much Greek? I'm trying to be as simple as I could, but I need to find out. Are we following me, please?
Yes, we are.
Okay, glory to God. So when we've seen regression. The other one now is classification algorithms, where you can have two classes, maybe things like yes and no, true or false, fail and pass. When you have that binary, you say this is dichotomous. But it could be more than two, it could be three, it can be four. So whenever you are dealing with discrete data, that is non-numerical data, the kind of supervised learning, solution that you propose when your output is non-numerical are referred to as classifiers. They classify into groups. So when you want to do evaluation regarding classifiers, then you start talking about accuracy, talk about precision, and you talk about recall. So to understand the next things that I want to say, I will just draw a table here, a 2x2 table. When you see a 2x2 table, we can decide to refer to it as a matrix. Okay? So I'm going to call this a matrix. And then I'll come to this middle part and erase this. So we can decide that what we have here are the predicted values, the estimates, the prediction made by the machine learning model. And what we have here are the actual values. So if here what we have are the actual values, and then here we have, say, true, and here false. And then for the predicted values, we also have true and false. It means that in this space, we have a matrix because we have rows and columns. So this matrix is called the confusion matrix. And as I said last week, even though jokingly, I said, don't you expect a confusion matrix to confuse you? But that's just by way of making sure that you take a look at it with so much seriousness. So if we do a bit of, tweaking of this, okay, and we say that this T is positive and this F is negative, then we can say this space is true, predicted, positive. Okay? Then this one will be true. Something is happening to my whiteboard. Okay, so this first one is true, positive. This one is true, negative. And then when you comment, is this true, negative? No, this will be false, negative. False, negative. So this will now be true, negative. And then false, positive. We are still going to see the implementation of this in a practical example. So here we have false, positive. So invariably, if you are calculating accuracy, your accuracy is all of the cells where you are positive. That is true positive plus false positive divided by the whole data set. Okay, I can say divided by n if I like, where n is true positive plus true negative, false negative, and false positive. So I'm going to leave this at this. But remember that we said if it is regression, we are trying to minimize the error. But if it's classification, we are trying to maximize the accuracy. So I want to leave this material and pause for a while to see if I can get feedback from us, so that I can now go to today's lecture and then we'll continue from there. Any feedback, please? No feedback. Okay, good. So if there isn't any feedback, we are going to take it like at least so far we understand. Welcome, Felicia Fatoki, Adedeji Adeshina. If you've missed anything, those things that you have, Obos, Ismail, and everyone, some of those things that you have missed, I'm going to go back to them as we try to cover two materials within the time that we have. The first part of the material that we are going to cover is just to show you that some of the things I've just done now are practically the same thing in the notes. So we'll go back to last lecture where we were looking at machine learning and we used this material. Okay? Data science fundamentals. We define machine learning as a branch of AI that enables systems to learn patterns from data and make predictions without explicit programming. So usually there's a program that the computer runs for a specific task. But in machine learning, it learns from data and performs that task which you did not program it for. So as earlier mentioned, we have supervised learning where we have labeled outputs. We have unsupervised learning, which are labeled where they find patterns. And then there's reinforcement learning, where the agent learns by interacting with the environment. Below are the real-world application of machine learning, and there are many more. Then we said under supervised learning, we have regression and classification. And we gave an example of regression to be predicting the price of a house because the value of houses are continuous in values. Then we use spam detection, whether an email is spam or ham, which is in two categories, as a classification algorithm. So it means that if I'm trying to predict the price of a house and I want to evaluate it, I'm going to be checking for low, error values. The lower the error, the better the performance of the machine learning model. Then if it's classification, I'm going to be looking for accuracy and some other metrics that we'll talk about later. And the higher that value is, the better. Then for unsupervised learning, which we have said that we're going to look at in week 8, that one has to do mainly with clustering and then dimensionality reduction. We'll push this to that lecture. But don't forget that we are not talking about whether there are labels or no labels. We are talking about finding patterns. So last week, we took an example of a supervised learning model. We called it decision trees. And we said that these decision trees can be used for both classification and regression. How do we distinguish between the two scenarios? When the outcome that you are looking for is numerical, then you are using decision trees as a classifier. As a regression model. When the value you are looking for is numerical. But when the age and income as we have here, so this is basically decision tree regression because we are calculating numbers. I mean, strictly numerical values or continuous values. Then, if it is going to put the outcomes into different groups, then we'll be talking about classification. So in this example, we are looking at two variables. They are age and income as our independent variables, as our predictors, as features that will determine the likelihood that somebody will purchase a house. What is the chance? We want our machine learning model, in this case, decision tree regression, to understand from data when it's exposed to it, and then predict whether somebody is going to purchase a house or not based on the age of the person and the income. What makes this to be a regression model? It is because what we are predicting is a continuous value. That is, we are predicting, the value of the purchase. If we are predicting whether the person will buy or not, then that's classification. But if we are trying to estimate the price and we are taking decisions at every price value, whether price that has to depend on income and age in this instance, or even more, variables. So where did we end the lectures and where I want you to technically end the lectures? I think technically, it is where we looked at the advantages and the disadvantages. What follows is just our implementation. And really speaking, the R implementation cannot come to us quickly since it's something that we are still learning. If you go to our notes that we have used today, you will see that some of the things that we are going to, replicate in the material are things that are already taken care of. For instance, we need to load libraries. These libraries are the tools that you will use for your analysis and data machine learning stuff. The business problem in this instance is to predict the price of a house. Suppose you have a client who wants to buy a house in, say, Ibadan, and the person wants to know the cost of a house at Bodija. And rather than using human intelligence, you now want your machine to learn. What you will need is to go and gather data. So first, you have understood the business statement. That is the problem statement. The problem statement is predict for me the price of house at New Bodija, Ashi, or whatever. That's the situation. I don't want to buy the house at a loss. I want to optimize the amount that I pay for the house. Because if I pay 1.5 million per annum and the house is about 1.2, and I have to pay for like the next 5-10 years and I'm doing business, that means I've paid more than the value of the house. But your machine learning and data science techniques can help you to pay a price that is, optimal, that is closest to what it should be. And once you begin to check the performance of the model and you see that the error is small, the difference between what is predicting and what the real value is, then you know that it's already doing well. Okay, so you collect data. And in the example that we looked at, we were not going to collect data, but we're going to simulate data. So in this create a sample data set, we are creating artificial data. If you recall, when I was sharing these notes, I said that you could get data firsthand by collecting it yourself. You can get data from an archive or from, somebody else's work, or you create artificial data. So in this example, the collection of our data is through artificial means we simulated. That's what's happening here. So the next thing that we could have done, if our focus was data analysis, okay, main focus, we are not going to spend time pre-processing because the artificial data that we created is most likely going to be clean. Okay, we've already set the boundaries, we've given it instructions. So having missing values is going to be a bit, how do I put it, difficult to experience. However, it's important that at the pre-processing stage, we learn what we call data wrangling. So data wrangling was our second lecture. So the curriculum has been, prepared in such a way that in the first session, we introduced you to the R environment and did a bit of R programming. In the second lecture, we were teaching us pre-processing. That is how to, format your data, how to deal with the data so that it will be in a proper structure. Going back to our problem, here you see that we have moved straight to training. Then you wonder, why did we jump the other steps? Because our aim in this class is not data analysis, it's data science. So, because we only have 10 weeks to cover this, we did not spend much time doing EDA because we are going to do EDA as we continue. EDA is just summary statistics, which we have even done, looking for the median, the mean, the standard deviation, the quartiles, and all of those things. That's what we call exploratory data analysis. We've also done visualization where we're using the ggplot2 to plot different types of graphs. It was last week that we began to build models. And we said, in terms of building models, we'll be doing machine learning. Once we select the model that we want, last week, the model that we decided to use is the decision tree model. So that's where training the model becomes the next step. So we've selected our model, we will train the model. How do we train the model? We create an object, which is this model. And then we use the R part function, that is R partition function. So what we expect is that we look for a function that will partition our data into different categories. And then our dependent variable, what we are trying to measure is purchase. And then in the independent variables that are in this data are income and age. So if you see in this data frame, there are three variables, age and income, and the outcome is purchase. So that's what you see in this. And then we now plotted the graph. And if you remember last week, we had that graph and we tried to explain it. So what we now went on to do is that in the real sense, knowing that we are going to calculate mean squared error or mean absolute error or other forms of error when we are doing regression. Okay, we now decided that it would be nice to also quickly talk about classification. Maybe that's where the confusion came in. Even though we set out to do decision tree regression, we went on to quickly talk about classification. And it's in classification that we started talking about this confusion matrix and all of that. So what happened was that once you get here, it's like everything changes. Because if you go back a bit, you will see that what we started with is to say, train the decision tree model. Okay? And we are looking for an output that is yes or no. So even though we were saying initially that we could have regressors or classification, in our implementation, because our output is yes or no, we are not going to use a regression model. We are going to use a classification model. That was why we started talking about classification in supervised learning. And then we said there are examples of classifiers. Last week, we talked about decision trees. This week, we are going to talk about random forest. Random forest is like decision trees. The random forest models are aggregates of decision trees. That's why we call them ensemble techniques, like having many trees, not just one trees, several. So if that was the confusion last week, the idea was to try to see if in one stretch we can cover decision trees, talk about them as, you know, regressors or classifiers. But in the practical example that we were not patient enough to talk about, we were predicting whether a customer will purchase a house based on age and income. So if the customer will purchase, if we are focusing on the value, then we'll be talking about regression. But the way this problem is structured, we're actually looking at, will the customer purchase or not? So we must use classification technique. So this is about classification techniques. And when you use classification techniques, it's important for you to evaluate the performance. And that was where we now began to talk about accuracy, precision, recall, F1 score, and confusion matrix. We will come back to this towards the end of the class. So what you now saw in the implementation was the splitting of data into test and train. And we said 80% of the data should be used for testing, for training, and the remaining 20% for testing. We made predictions, and we ended around this point. And I can appreciate the fact that ending at this point could make a lot of us, you know, have issues with interpretation of this whole, you know, content. So whereas I don't intend to explain this content in this lecture, in the next algorithm that we are going to look at, I will take my time to talk about precision, recall, accuracy, and F1 score. On that note, I want to pause and give us, you know, opportunity to make remarks so that we can move to today's lecture. And if there are no remarks, I think it would be nice for us to take like 3 minutes break so that we can then move on and look at today's lecture. Let's go back to the class and find out if what we have done now is an improved version of last week's lecture. Hello. Okay. So granted that we've not talked about confusion matrix, we've not talked about sensitivity and co. Let's take 5 minutes break. Okay. Let's all take a break. Take some water because I need to take water. And then we'll go to today's work. See you in 5 minutes. Okay. All right. Yeah, welcome back. So we move to today's lecture. Welcome again to Data Science Fundamentals and Introduction with R. This week, we are looking at random forests and assembly techniques. So what I hope you can still see my screen, class.
Yes.
So what I'm going to do is I'm going to download this file again. The goal is that it will be easier for us to follow now or later. Okay, so I've downloaded the folder, the file. Then I'll go to WhatsApp. I think our group is FSS. Yes, and then I'll upload it to the group so that you can download on your system and then just upload it on your R Studio. Okay, so if you were going to upload it on your R Studio, you go to your R Studio. Okay, so you go to File, then you click on Open File, and then Browse. For me, it's in my downloads. So if I go to my downloads, I'll see the file. But now I can't. Okay, this is it. 708. So if I pick it and I open it, it will open the file for me. This way you can easily run the file, which is the less difficult part of the whole thing that we are looking at today. So if that is what is going to make it difficult for us, this is one way to overcome that challenge. I haven't done that, believing that when you refer to the video, it will be easy for you to replicate what I've done. I'm now going to close this and go back to the classroom and open this PDF file. In terms of trying to reinforce the learning, one way is to keep coming to this platform and checking out the resources. Okay? If you're able to get the R code and read the notes, and then maybe, ask LLMs to provide you further explanation, that will help you. So we'll continue with machine learning basics. But today we are looking at random forests and ensemble methods. So what are ensemble models? They are models that combine multiple models. For instance, in terms of random forest, it combines several decision trees. And in layman's language, we can say a forest is an aggregate of many trees. The goal is to improve the prediction accuracy. Now, we are saying prediction accuracy because our focus is classification models. Remember, we are looking at machine learning. And under machine learning, we have supervised learning, where the outputs are labeled. Under supervised learning, we have regression and classifiers. The difference between regression and classification is when you are predicting an outcome that is continuous, you use regression. But when you are predicting an outcome that is discontinuous, that is discrete, that's categorical, then you use classifiers. If you are dealing with regression, you measure error. If you are dealing with classification, you measure accuracy. In regression, the lower the error, the better the model. In classification, the higher the accuracy, the better the model. Okay, so remember, we are combining many decision trees that classify to get a random forest that also classifies. The goal is to improve the prediction of accuracy, making sure that accuracy is high. Secondly, I talked about overfitting. Let me try to put that in, just to repeat. When you split data into two, for instance, you have your training set and your test set. If you check the performance of your training set and it is high, and then the performance of your test set is low, then what you have is overfitting. Overfitting is when your model does well during training, and doesn't do well when it faces new data. When you expose it to new data and it's not able to do well, it's a problem in machine learning, and there are ways around it. Then the idea of variance and bias, still in this same discussion, is the fact that if your model is performing well, if, for instance, the difference between the prediction when you are measuring error and the true value is small for a particular instance, then you say the bias is low, because that's what you want. You want low bias. But some models are able to give you low bias, but the variance is high. What then is variance? When it's exposed to different scenarios, and even though the bias is small, but the values have large differences. So if you are predicting 3.0 and it gives you 2.9, you predict 3.2, it gives you 3.1, then yes, the bias is low, the variance is not much. But if in a particular time it's giving you 2.9 and then giving you 5.5, and then it varies, that's variance now. Even though the bias is close, but it varies, then you have a problem at hand. You cannot achieve low variance and low bias. You have to compromise. So we have what we call the bias variance trade-off, which we'll return to later. But just to help us, using Ensemble techniques will help us to reduce overfitting and solve the problem of the interplay between variance and bias. What are then the different types of Ensemble methods? There's bagging, there's boosting, and stacking. We'll look at each of them, of these, as we proceed. So, why build Ensemble methods? And then we'll now look at these three distinct techniques and see if we can understand the differences. We use Ensemble models when we want better prediction. So the same challenges that we talked about in the earlier slides are equally the reasons why we have to rely on a technique or techniques that gives us better performance. We cannot rely on a computer to do stuff for us without ensuring that its performance is very high. If you leave a machine, maybe a robot, to attend to patients in the hospital, whether physically or virtually, then you must ensure that before you deploy that machine or robot to the world, the performance must have been proven to be very high. So instead of using like decision trees, then you are better use Ensemble methods that will give you better results. Secondly, we've said that overfitting is a challenge with machine learning models. So to reduce, not to eliminate, to reduce that problem of your model performing well during training and not doing well when exposed to new data, we need also to use Ensemble models. And how do we do that? They are able to find, the mean around many models. That way, you would have reduced the noise that makes your model to not only learn the trend, but learn things that are not essential. What am I saying? We used an example last time, and we were saying that if somebody knows how to drive within your institution, I hope that's the example that I used. Somebody is able to drive well within your institution and he has perfected it. And then you now put the person in a different environment. If that person does not perform well, then we say that there's a problem of overfitting. But if somebody learns in your environment and then you now take the fellow to another environment and the person is able to do well, then you say, yes, you have reduced overfitting. Okay, so by using many decision trees, you can reduce that problem. Finally, if you use Ensemble techniques, you have a more robust model than individual models. You know, in human relationships, we say that two good heads are better than one. So that's the idea. If you have one good model, good enough. But if you have several models that can be aggregated and then you're able to produce a better one, then you'll be sure that you want that latter one than the former. So as mentioned before, what are the key techniques? We mentioned them, but what are the differences? When you talk about the bagging technique, what happens is that you are going to combine the prediction from multiple models, but you make sure that you train those models on different subsets of the data. Remember that in our notes at the start of this class, we talked about training and testing. And now you divide your data into 70 and 30 and all that. But we said this must be done randomly. Yes, by using random techniques, you reduce bias, but you still will have bias. So to further reduce the bias, you can now break your data into different subsets. And then you build many individual models, maybe many decision trees. You train one on a different subset, it learns from that subset. You use another decision tree on another subset, and it learns from that one. And by the time you pull them together, then you should have a random forest model that does better. So you combine predictions from multiple models trained on different data sets. Bagging is like putting them in different bags. So if you want to explain this to a layman, it's like saying, okay, you have all the data, but you now bring bags and you just split the data randomly and put them in different bags, expose them, to different individual decision tree models, and now combine their predictions. That's bagging. But boosting, what you do is you train the models in sequence. You have several models, but you train with one model and then you introduce that into a new model and then you perform training again. And you should expect that if you have used one model to train and that model has learned the patterns, by the time you introduce that other model, some noise would have been reduced in the earlier one. So whereas that one is putting them in different bags and then you run them separately and then combine their predictions, this one is like in sequence. You have models that are sequential and then you train, you introduce to the next model. But you'll be focusing on the weak predictions so that, you've seen the prediction at first, and then when you introduce into the next model, you expect the prediction to be better. So the goal is to see if prediction is improving. If it is not improving, then using boosting is a waste of time. The last one is stacking. What does this do? This one combines multiple different models into a meta model. So it's like bringing all of them into one model eventually, which you use. So when you say you are stacking, it's like you are piling up. You have one model, you put another one on top, yes, another one on top, and then you now have like a collection of several models, and then you can now expose it to that collection. I hope that makes sense. But for more, context into this, there will be opportunity to give us resources by the end of this class. So let's now introduce us to random forests. Now we have to pick up the pace so that we can, really do the implementation. So first, random forest is an assembly learning method based on decision trees, like we said. It builds multiple decision trees and averages prediction to improve accuracy. And it can work well for both classification and regression problems. How does this work? So here we are using a boosting process. Okay. So we say this is bagging. Yeah. Select a random subset of data to help us. We'll go back a bit. You have to go back a bit and see that bagging is bootstrap aggregation. Okay. So if we come back to where we are at the moment, where are we now? Okay, yeah, good. How does random forest work? First, you have to, split your data set into random subsets. Then you build several decision trees independently. This is where this bagging is different from stacking, because in stacking, you pile them up and then use them, together. So build a multiple decision tree independently. Then it is the predictions that you now aggregate and find their average. We will see that in the what we call classification reports or confusion matrix. So that's how it works. What are the advantages over, say, decision trees? It reduces overfitting by combining multiple trees. It's able to handle data set with missing data. So it's also possible to use random forest techniques to do data wrangling. Then feature importance, it identifies variables that are key for the purpose of prediction. I said that, let's go back and recall what we said in one of the whiteboard screens that we talked about earlier. Let's see if I can get that. Good. So when we're looking at this data process end-to-end pipeline, okay, which we did not even conclude, because we can also say after evaluation, you can now deploy your solution. It is when you deploy your solution that it becomes available for other people to use or for you to even use. So we said that when we get to training and testing and we check our performance, if our performance is not okay enough, if it's not what we expect, we can go back and then we use a different model if we care. Say, for instance, you've used decision trees and you see that this overfitting problem is occurring. You are seeing good performance in training or poor performance in testing. Then you can go back and change your decision trees to random forests. That's exactly what we are talking about. Okay. And in trying to do that feature engineering, you can identify variables that are really contributing to the prediction. You can, match them together to produce a new variable, or at the end of the day, know which variables to focus on. Tweak your model and function, and then do training and testing again. Also, random forest works with large data sets. So when you have high-dimensional data, what is it that is important about high-dimensional data? Which is also a very important issue in machine learning. And that's why I said we are still going to talk about dimensionality reduction. One major issue is this high-dimensional data. Sometimes in some fields, it's difficult to get data. Okay, very difficult. Elon Musk, I hope we know him, has this company called Neuralink. And what they basically do is to put a chip in your brain so that it can read your thoughts and then help you to take actions. But not many people are going to commit themselves to be used for that experiment. So the training data set in such situation is usually very small. So when we have our normal spreadsheets, on the columns, we have our features. X1, maybe age. X2, income. X3, gender, and so on, up to Xn. Let's assume that this thing ends at X100. You could have more than 100. And then at the end of the day, here you have your observation. First person, second person, and let's say we are only able to get 50 patients. So when the number of features is more than the number of observations, that's a very big problem in computational statistics. Okay? So there will be need for you to work on these features. And one way to do that is you can use the random forest model to determine the features that are contributing the most. So that's what you see here when it says it works with large data sets and scales well for high dimensional data. That is, not just having several observations, because the issue about large data sets can be the number of observations. This can run into hundreds of thousands. But when you have high dimensions, many features, that's a bigger problem. But if you are faced with such and decision trees is not giving you good results, you can fall back on random forest. That's what we have here. All right. So this is now the implementation. So instead of going through the implementation in this our PowerPoint, okay, this PDF, we'll instead go and run the code. Okay. But let's talk about these tuning parameters for optimal performance before we go to our code. The parameters are still the features. And when we say high dimensional planes, we have high dimensional data. We are also talking about when we have high level of data, high parameters, plenty of them. So we need to tune. How do you tune? One, you have to know the number of trees, the number of trees in the forest. You have to know the number of features that we randomly select for splitting. So now imagine that the number of features is way more than the number of trees or the number of observations. Then we start talking about hyperparameter tuning. So is that hyperparameter tuning that is discussed in this tuning random forest in R? Why would that be necessary? We go back to what we have seen earlier when we were looking at the pipeline of a full data science project. And we said after training and testing, we realized that our model is doing well with training, but not doing so well with testing. We work on the features. We realize that part of the problem is that there are too many independent variables. High dimensional. We tune it. So that's what you see in this tuning random forests. Let's go to our R and wait for feedback. Any feedback from us? Are we okay? Okay, so I tried to run something before. Don't forget, again, if you are not yet used to this, R console, and this portion is the R console. When you download R, this is the only window that you can work with. But in R Studio, you have 4 regions. So I've attempted to clean everything. Let me go to the class and listen to us. It's not 2LD not to listen to the participants. I hope I'm not speaking to myself. I've lost track of it now. Where is the class? Is the class still here? Hello?
We are still with you.
I can't even locate the class anymore. Where did I use for the class? Wow. I can't locate the class. Okay, so is there anything or should I just go on, sir? Somebody to help me.
Let's go on.
Okay.
We're getting it.
Okay. Thank you very much, sir. So we'll go to our R, and then we see that it's going to be easier now, because if you have loaded the data, then all you need is to run the code. So I hope I'll be able to get to the end. I won't be in a hurry. If I get to the end, that'll be fantastic. So if I undo this hashtag, I will see what is here. Building a random forest model in R. So when you put that hashtag, it turns it into a comment. Okay. So that gives us like the heading of what we are doing. Then the next thing is we want to load the necessary libraries. Okay. We are bringing the libraries into your projects. So we'll run this random forest library and the carrot library. I wish that we could also run it, but we said before that if there is a library that you run and is not already installed, you can go and do install.packages. And then I think for some of us, it might be that we don't have the random forests. I think we have done carrot before. So that way you can run this line of code, but I'm not going to do that because I already have random forests. So now it's like we have gone to the library and we have fetched random forests and we have fetched carrots. I think in our next class, we will need to show you how to now bring in real data, even though I already have a file that I will send to you maybe after next week's lecture, which will be a real practical, implementation of not simulated data, real practical implementation. And then we'll do all those end-to-end data science pipeline. And then those lessons will now become, easier for you to understand. Train tests, overfitting, validation, classification, and all that. Confusion matrix, they all come to become easy. So when in line 8, what we are doing is we are creating artificial data. And we said, because we are creating artificial data, and we want to pick random samples, which will be consistent with the ones that everyone will pick, then we'll set a seed. The number you write in this seed will determine whether, if somebody repeats your script, whether that person will get exactly the same result. You do this when you are using artificial data, when you are simulating. You don't need to set seed when you are using real data. So if I run line 9, what it does is it has recorded that 42 as the code that it will use to randomly select values. Line 10 will be completely unnecessary. Line 10 to line 14 is irrelevant if we already have a data set. If there's whether primary data or secondary data, we will not be creating the artificial data in lines 10 to 14. We are creating an object called a variable, if you like, df, and we are using the data.frame function to create like a spreadsheet that will have 3 columns, whose columns will be age, income, and purchase. And then it will pick samples of age from age 20 to 60, 200 of them, and then create income, 200 of them also, but the income will be from 30,000 to 120,000. And then randomly have the outcome, which is purchase, and the values will be yes or no. So because these outcomes are labeled yes or no, it's a supervised learning algorithm. If we didn't have this label yes or no, then we will be using unsupervised. Secondly, we have yes and no. They are not numerical values. So we are not doing regression. Instead, we are doing classification. So that's what happens between line 7, line 10, and 14. Okay, good. Now, we have purchase. Our purchase is yes and no. Yes and no. So what we want to do is we want to convert that yes and no to factors, to zeros and ones, more or less. Because it is then that our model can interpret. If you don't convert to those numbers, the yes and no will not be sufficient to train our model. So what do? In trying to convert, we'll pick our data frame, which is df, which we can run and see it here. This is our data frame from 1 to 200. And then the first column will be age. The second column will be income. and the last column will be purchase. So what we want to do here is we want to pick this purchase and we want to convert that purchase to factors. So we use the as.factor function and then take the whole data frame, focusing on the column which is purchase. That's what is happening in line 17. So in line 18, we now want to train the model. Okay? But before you train the model, you need to create that model into an object or a variable. So what is that object here? Our object is model underscore random forest. That's the name. You can put any name there. And then you pick the function R random forest. Last week, we were not using random forest. We were using the R, let's just go there. We were using the R part. And then we knew that purchase was our dependent variable. And age and income were our independent variable. Because here we're doing decision trees. This week, we are using random forest. And if you check, we are still there with purchase as our outcome, age and income as our predictors or our features. The data is still TF, then the number of trees is 100. So when we do this, we have created or fitted our model. And line 21, we want to see how it looks. We want to check the performance. What do we see? Let's check the results together and see if we can begin to interpret the results and then begin to do some calculations. Begin to talk about, some of those metrics like accuracy, like precision and co. So let's take our time. Here, it just calls what we have done. What you see here is just this line 20. It says we have used random forest, and the formula is y is equal to age plus income. We have used the data that we artificially generated, which is data frame, and we want the number of trees to be 100. The random forest type that we are using is classification and not regression. So it still goes to tell us the number of trees. So what do we see in the result? Let's cancel this. What do we see in the results? We have a confusion matrix where we have no and no. No and no. They agree. So this is true negative. It is true. Okay. Then here we have yes and yes. So we normally say that these diagonals, you add these diagonals together, and let's see if we can get a calculator. Let's get a calculator and see. So if we want to calculate accuracy here, we will say 56 plus 59. That's 115. And then we expect that everything is 200 because 41 plus 44 is 85. So 115 plus 85 is, I don't like the way this thing is arranged. So you see here that we have no before yes. What am I saying? Let me go back and show this. If we come from here, it will be better for us. If we come from here, where we have that confusion matrix. Thing is not okay. Good. So this confusion matrix. What we have here is yes, no, yes, no. So it is this diagonal that we are going to use to check our accuracy. But if you check the output of our R, unlike what I said before, which was wrong, we are supposed to use this diagonal. So it is this diagonal of no, no, yes, yes. Let's just check what our calculator will give us. I'm now not really convinced that I made a mistake earlier on. So let's go back to calculator. That output is a bit confusing for me. So I'll say calculator, please calculate for us the sum of the major diagonal. Let's do 56 plus 59 gives us 115. And then when we divide that 115 by 200, we get 57.5. That's 0.575. So what we see here is 42.5, which is 44 plus 41 divided by 100. So if you go to your calculator again, and then we do, it's just the orientation of the result that is giving us problems. If we do 41 plus 44, that will give us 85. If we divide that by 200, we'll get 42.5. 42.5. So we'll get this 42.5 as the accuracy because the orientation of this thing is reversed. So rather than adding 56 and 59, if you swap yes, no, and you swap yes, no, you have 44 and 41 on the major diagonal. I hope that makes sense. But let's just continue. If it's confusing, I'll still come back to it because I actually want us to run the entire code. So what follows here is the visualization. But please don't forget that because it's a confusion matrix, there are 4 possibilities. It's either you predicted true that the person will purchase the house and the person did purchase, that's true positive. Or you predicted that the person will not purchase and that fellow did not purchase, that's true negative. It is true positive plus true negative when added together that you divide by the total sum of data to get your accuracy. And in this example, we are getting 42.5%, which is the same result we got when we changed our orientation and we decided to add 41 to 44. So we go back to one of the things that we also said in the early part of our lecture. What was that? We said that in the end-to-end data science pipeline, we have visualization. And that for data analysis, visualization is part of exploratory data analysis. So if all you want to do is data analysis, inside your exploratory data analysis, you should use some graphs to show the details and the patterns in your data. But now we have gone to building model, training and testing. The kind of visualization that we are now doing is not the mere visualization of the structure of the data, but the visualization after we have exposed our data to our model to the data, it has learned from the data, and then we now want to see some of the outputs in the form of graphs. That's what this visualizing a decision tree in R means. Why are we not doing visualization in random forest? Don't forget that we actually want 100 trees. And if you recall from last week's lecture, when we tried to build our tree, let's even try to build our tree. Let's run this code quickly and then show to us what we'll get as output. And then imagine what you have. Look at what we have here now. This is just a decision tree. So imagine we have hundreds of these. It's not going to look decent. So we would rather build one decision tree for learning purposes. So that is why eventually in this practical visualization, we are visualizing a decision tree. Even though random forests are made up of multiple trees, but we can visualize a single tree using R paths. So the code for visualizing a decision tree is what you see here. And that is what part of what we saw last week. So I'm going to erase this tree and then go and run the R paths as though we are doing last week's work, then the R plot. Then we train a single decision tree. If we are training a single decision tree, we will not be using random forest. We'll be using the R path function. So when we run line 30, we store in that tree model. And then we go on to plot the graph. And then we have this tree. So we did this to show you that if you are going to visualize a random forest, you need to visualize hundreds of these. If we go back to our notes that we showed you, never mind, I keep going back to this, my whiteboard. Yes, I have to. Because I actually want us to really understand this end-to-end process. Because in week 9, like we said, you are going to have a project. We understand the problem statement, we collect data. If it is primary or secondary data or data from archive or online source, there might be need for you to process it. Sometimes they come clean. Then we check the structure, we check the patterns, we do some preliminary analysis, EDA, which we can add visualization to. But more visualization will come later. Then based on our visualization, we will check whether we will now know what kind of models that we can use. For instance, we said, let's try a decision tree. And then we see the performance that is not going well. Then we can go back and improve it by using, an ensemble technique, for instance, random forests. So why did I go to that? I went to that because when I saw the next line of code that we're going to be looking at, we said,
Hello, sir. Okay. Should get the other.
Hello.
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 Don't come to our okay.
I guess the problem is from his end.
I think the network is down at the end.
Beside our class, HOD's office.
Hello, sirs. Hello, Mars. Hello. Hello.
Hello, sir. Welcome back, sir.
Okay, sorry. Is this electricity wahala? You know Nigeria now.
I think your network was down.
Yes.
Okay.
They took the power. So I had to
Yeah, that's Nigeria.
Sorry about that. Yes. But let's see how we can manage the remaining 5 minutes to do something really tangible. I just hope that we've learned something today. It's my desire that we learn a lot. So let me try to do something like 3 minutes, because I promised to share some resources with us. Even if I don't finish this material, I'm glad to repeat part of it next week, because whatever we are doing next week is still similar to what we are looking at now. We're only looking at examples of machine learning models. So I don't know when. Can you see my screen? Can you see my screen, please? Hello, everyone.
Wow. Yes, we can see your screen.
Okay, thank you very much. Thank you very much. So let me go back a bit and see if you recall this place. Remember that we said we wanted to do visualization, and we chose to use one tree. And we ended up having this graph here. Okay. So I went on, I don't know, let's assume that the thing now went off there. So I said we need to tune our random forest. Why are we tuning? So that we can have better results. So we decided to call this the tune_RF. Okay. So what I will do from 9:35 to 50 today is to just run the code and speak to it. But the first thing I will do in next week's class is to slow down and explain some of these things, because I really still want to attend to the question that was asked today. Very important to us. So in line 35, we create the tune_RF model. Oh, so because internet went off, I have to start afresh. Let me start afresh and just run the code. So I have to go back and run from scratch. Let's just go. So we run that. We have the plot. We have the plot. Very good. So we fine tune. Okay. And then we make predictions. I'll speak to this later. Then we do our confusion matrix. And the confusion matrix will give us this table. Can you see the prediction now? It's a lot better. Then we'll also do variable importance. That will give us a plot also. These plots are not so great because we don't have, enough data points. I will speak to this next week, like I said. Then we print that same confusion matrix, check the error rates for each of the stages of the model, and then I even get the correlation value. So don't worry from line 35 to the end. Maybe it was good that the electricity was disconnected by those who own electricity, because there's really something that I want to show us. So I now want to, since we are getting to the end of this program, 10 weeks is not enough for one to do data science and master data science. You need a lot of resources. If you ask me, what's my opinion? I would say when you have properly digested this, you can discuss with your rector, discuss with Professor Lubuseye, so that we can scale up the training. However, there are a lot of us who couldn't meet up with the classes. The good news is that we have the videos. If you watch the videos and you are able to master this level, then we can build on it. Having said that, if those things don't eventually materialize, you can try W3 schools. And I'm introducing W3 schools to you, not just for you to learn data science, but to learn a whole lot of things. For instance, you can learn R programming. Okay. So let me see whether we can get R programming. This is the one I'm showing you today. Next time, we'll show you other sources. So you can use this to upgrade your R programming, capabilities. So that when next we are coming to maybe perhaps teach us maybe the part 2 of this R will not be a problem. Okay. So I'm going to copy this code, this link, put it in our WhatsApp group. And I think with that, I've answered the concern of Dr. Adeshe. How do we improve beyond this particular class? One, we'll go to our channel, YouTube channel, and watch other resources that Prof. Olubuse has. Complimentary lectures. You can't learn data science in 10 weeks, but you can begin to learn data science. So in conclusion, I hope that when we are done with this, and when we have completely digested the content, even though we have not finished, we'll go back to meet our, our principals, where you have a principal, I have mine too. And then we'll look at how to, add more value. Thank you so much. I'm stopping the recording. If there are concerns and comments,